Welcome back. This is graph traversals. It's homework number 11. So here's the homework. This is posted already, right? So let's see. I want you to look at some code that I've got posted, graph CPP. I want you to get it working. Then I want you to modify the code to work with this other graph. Then I want you to look at this hand execution that I've already done for you and modify it. Okay, and then I want you to use an even bigger graph and do something to that and a couple other things. So there's lots of things we can do with the graph. The classic problem that's talked about is the traveling salesman problem, and there's variations on that, and I talked about that in the previous video a little bit. But before we do that, like the simplest thing that you'd want to do to a graph is just traverse it, right? Just traverse it, just see what's in the graph, okay? So there's two ways to do a graph traversal. There's a stack traversal, also known as a depth first traversal, and then there's a queue traversal, also known as a width first traversal. So the way I think about this is, like, if you're a football fan, it's a little bit like a passing game versus a running game, although not really. But like, let's say you have a graph. Let's just make a little cloud here. That's the graph. For the stack, you're trying to go as far as you can go before coming back, right? And so it ends up kind of looking, you know, very kind of spindly, because you go all the way out and then come back until you can go out again, and you come back until you can go out again, you come back, like that. But a queue, starting at the same center location, you sort of visit all the local guys that you can first. And then after you visited all your local neighbors, then you visit their neighbors. So it ends up kind of looking like this. Okay, so one is kind of more like a passing game, sort of, in football, and this is more of a running game. Not really, but this one goes as far as you can, as soon as you can, and this one kind of goes as close as you can, like everywhere you can, close kind of thing. Okay, so we're not going to do a queue, we're just going to do a stack. But anyway, that's the difference between the two. So here's a graph that I've made up, this little guy right here. And the first thing you have to do is choose a node as a root. So here I've chosen C as the root. Okay, and what a stack traversal does is it turns a see, there's a tree in here. So notice that this is a tree. It turns a graph into a tree. Okay, and well, that's what this one does too, but the stack traversal, you get this sort of spindly tree like a wisteria, and over here you're getting, this is more like a rosemary, right? Kind of this bushy little tree. But they both turn graphs into trees, both of these traversal things. And the other thing about them is the starting node determines the tree, determines a specific tree, I guess. So here we're going to start at node C, and if we start at node C, we get a particular tree. All right? If we started at some other node like A, we'd get another tree. But anyway, here's the algorithm. It's pick any starting node C, push the node, then select a neighbor at the top of the stack, push the neighbor. If at the end of the list, go to 6, otherwise go to 3, pop. If stack is empty, we're done, otherwise go to 3. So we'll go through that a little more gently. But look, here's the adjacency list. So we've got an array of these nodes that have a data element in them, and then they have a pointer to the next node, which is a neighbor. So this is just the graph stored in here. So let's just check real quick. So A has neighbors B and C. A, B, C, there it is. Okay, A has neighbors B and C. And B has neighbors A and C. So on B's row, we have neighbors A and C linked on. And C's node, we have neighbors A, B, D, and F. A, B, D, F. Let me just check the whole thing real quick. D has C and E. D has C and E. E has D and F. E has D and F. F has C, E, H, and G. C, E, H, and G. G has F. H has F. Okay? So this is the first column here is every node. And then we have a list built off of each row here that has that starting nodes, neighbors. It's an adjacency list. It's a list of neighbors or adjacent nodes. Okay, so we'll start at C, okay? That's arbitrary, but that's what we're doing for this particular guy. It's just, I chose arbitrarily C. And you push him. So we push this C right here. Okay, then, so that's step 1 and 2. Then you select a neighbor of the top of the stack, ignoring neighbors previously visited. So another way to say that is select an unvisited neighbor of the top of the stack. So the top of the stack is C. So you go to C's list, and C has these neighbors. He has neighbors A and B and D. So you just go down this list finding somebody you haven't visited before. Well, we haven't visited A. So we'll push A. So by the way, we have to keep track of who we visited, right? So you could here, let me go over here. So you have to keep track of a couple of things. First, who you visited. And since we're building a tree, we need to store that tree somehow. And an easy way to store a tree is just store the parents. So it's not a there are better ways to store a tree, but this is a compact way to store a tree. Is just store each node's parent, and that is a tree. If you store that, you'll see. So let's see. Let's start over. So A is the root. So we visited him, and his parent is null because you could say parent is C because he's the root. So our tree looks like this right now. It's just C. We push it. I'm going to start over again all the way here. You know that? I'm just going to start over all the way. Even though I have the answer right here. So we push C. Then you select the neighbor of the top of the stack, an unvisited neighbor. So you go down here and A is not visited. So we push him. And now we visited him. So we mark him as visited and we mark that his parent was C. So the tree looks like this now. C is the root. You could put arrows just to kind of show which way you came, even though it's not a weighted graph. But okay, then you let's see, what do? We push the neighbor. We're not at the end of the list, right? We're only here. So we go to 3. So we go back to 3. Select the neighbor of the top of the stack. The top of the stack is A. So you go to A's list and you find an unvisited neighbor. B has not been visited, so he's an unvisited neighbor. So we'll push him, right? We'll push B, mark him as visited, mark that his parent was A, right? Then go back to 3 and select an unvisited neighbor of the top of the stack. So you go to B, and you visited A, you visited C. So we're at the end of the list. Step 5, we're at the end of the list. So we go to 6. So we pop. So C comes off. Right? And then go to the stack is not empty. We're not done. So you go back to 3. So I'm not going to follow these so closely anymore. because it's tedious, but you should, but look, I'll just do it because I know how it works. So basically you're just finding an unvisited neighbor and pushing him. And then when you found all the neighbors, when you visited all the neighbors, you pop. Okay. And then you just keep going like that until the stack's empty. So we find an unvisited neighbor of A. So we visited B, we visited C, so we're going to pop. Okay, now the top of the stack is C, so we find an unvisited neighbor of C. We go to C's list to find out who his neighbors are, right? A has been visited, B has been visited, D has not been visited. So we push D and mark that he's been visited now, and you mark that his parent was C. Okay, then you go to the top of the stack, find a neighbor of the top of the stack. So D is the top of the stack. C has been visited. E has not been visited. So you push E. Mark that he's been visited. You mark that his parent was D. And you just continue like that. You're finding unvisited neighbors of the top of the stack. So the top of the stack is E. You go to E's list to find his neighbors. We visited D already. We haven't visited F, so we push F. Well, we've pushed F, so that means we visited him. So we mark him as visited here, and we mark that his parent was E. That's where we came from, is E. Then we just keep going like that. We find a unvisited neighbor of the top of the stack. So F is the top of the stack. We start looking at his neighbors to find an unvisited one. We visited C. C's been marked. We visited E. E's been marked. We haven't visited G, so push G. C, D, E, F, G. Do you see what's happening? We're going as far as we can before we come back. Now we're going all the way down, as far as we can before we come back. I should be building the tree here. So we went to B here. Then that was the end of C's neighbors, so we popped. And that was the end of A's neighbors, so we popped. And then we pushed another neighbor of D. We went this way, and then we pushed a neighbor of D, went that way, and we pushed F, and then we pushed G. So now we've gone as far as we can this way. First we went as far as we could that way. Now we went as far as we can this way. So now we're looking for a neighbor at the top of the stack. G is the top of the stack. So we come over here. We look for G's neighbors. F has been visited. There's no neighbors. We're at the end of the list, right? So we go to 6, which means we pop. So we pop off G. Okay, now we're kind of backtracking. We're back to F. So you go to the top of the stack is F. So you go to F's adjacency list. And you look for an unvisited neighbor. So C has been visited. E has been visited. G has been visited. H has not been visited. So you push H. C, D, E, F, H. So we came back and then we went as far as we could towards H. Then look for an unvisited neighbor of the top of the stack. Top of the stack is H. We go to H's list to look for unvisited neighbors. We find F has been visited. So we're at the end of the list. So we pop. Now we continue. We go to F. We look for an unvisited neighbor, but we visited all of these neighbors, right? We marked all of these. Oh wait, I didn't mark some data over here. G was visited, and his neighbor was, his parent was F. I forgot to mark some data while I was doing this. H has been visited, and his parent was F. When you push H, you should mark him as visited, and you should mark that his parent was F. And likewise, when you push G here, you mark that it was visited and his parent was F. Should do that right after pushing on the stack, right? So you push on the stack and you mark visited and you mark parent just to store the answer, the final answer. Yeah, so anyway, all of these guys have been visited, so we're going to keep looking for neighbors. We're not going to find any, and we're going to pop. So E, D, C will pop F. Then we visited all of E's neighbors, so we'll end up popping E. And then we visited all of D's neighbors, so we'll pop D. And we visited all of C's neighbors, we'll pop C. The stack is empty. The algorithm is done. Okay, so that's the execution of a stack traversal of a graph, and it's a depth first traversal. That is, we started at C and then we went as far as we could go. We went all the way to B. And then when we couldn't go any further, we came back, and then we went as far as we could go. We went all the way to G. We came back, and we could go a little further this way, so we went that way and got picked up H and then came on back. So the resulting tree sort of resembles the stack execution, right? You go all the way out to B, you see that appear, and then you come all the way out to G. You see it going all the way out to G, right? Then coming back to F, then going out to H, and then backtracking all the way to the root. Okay, so so we started with a graph. We chose C randomly as the root, executed this algorithm, and the result is a tree. Okay, so the point of this is to visit everybody. Everybody gets visited. That's what we're trying to do, but we end up with this tree sort of as a side effect, and it's a depth first tree, a tree with long paths, as opposed to a queue traversal, which would have sort of stubby paths. All right, there's that. Okay, this is what I want you to do for the homework. I want you to do a stack traversal, so it's not so bad because I've given you the answer. So if you pull up this here thing, this CPP thing. Okay. It's the same graph that's in the notes that I just executed. So this two-dimensional array is this, well, here I'm using an adjacency list in the notes, but here I'm using an adjacency matrix, right? Just because it's easier to access elements in a matrix, but it's the same graph. Like here's row A, it has neighbors B and C. Right, I've labeled down here the columns B and C. Right, A has neighbors B and C, and C has neighbors A, B, and D. Right, where is it? C has neighbors A, B, and D. And and F. Here's F. What's this guy? Doesn't have H on there. Oh, this is not right here. Oh wow, I never noticed this before. I've been using this homework for like years, and I never noticed that there's a difference in here. This is what's in the notes, but in the homework assignment, the C has neighbor H. There's a link in here, and that's also H. Row H has neighbor C. Yeah, because these have to be. These are a mirror about the diagonal, right? If you imagine the diagonal through this, it's the same on either side of this, because if H's neighbor is C, then C's neighbor is H. So if H's neighbor is C, C's neighbor H. Anyway, it shouldn't matter. You get the same resulting tree because you find. Oh no, you wouldn't. You would find C's neighbor H. Yeah. Okay. Yeah, there is a little difference. All right. Anyway, that's fine. So you're going to get a slightly different tree. Anyway, this thing works. It's fully executable code for this graph right here with the extra link in there, the CH link. Anyway, I've got an array of Booleans where I'm just marking who I visited, which is this array here where I have the parent and the visited. I did two arrays for some strange reason. I did a visited array to mark who you visited, and then I have a tree array, which is the parent really. So I initialized it with -1s, but then you'd go through and you'd put A, B, C, D, E, F, G, H in here as you, or the parents, you'd put C, A, C, D, E as you visit. So this thing, the way it starts is, I have a function called fillofile, which, okay. I have this function that fills the data from a file. There it is. This graph1.text, I've got a function that reads that in and initializes this array right here, this 8x8 array. So you don't, I mean, here it's hard-coded, and I just overwrite this. But the point is I want you to use another graph, and I want you to read from a file. So that's what that's doing. So we're going to push C. We do that by calling traverse and sending it a 2 because index 2 maps to C. So I'm pushing a 2. So the point here is that this is a recursive function, and the recursive call mechanism is very much like a stack. There's something called the call stack in a modern computer, von Neumann architecture that we use. There's the call stack. Every time you call a function, values are pushed onto the stack, right? So there's a built-in stack in the function calling mechanism that we can use. So here I have a abstraction of a stack, but what we're really doing is we're doing the stack calls just by using recursion. All right, it's very, very important idea here. So yeah, so I call traverse, and so we come into traverse with item 2. Node list. Where's my pound def? I must have a pound def for where's node list? Graph 8.8. Oh, pardon me. Integer is the type. Node list is the variable. Sorry, I was mixing up another language, I think. But anyway, this is just a C that, or the 2. This is just the 2 that you pass in here. So we mark that we visited node 2, right? We put this X here on visited right here. We make this true. So we've marked that we visited C. Then I think for debugging, I'm printing out the node C just so I could see where I am in the code here. And then we're looking for an unvisited neighbor here. So we're walking through the adjacency list, which in this case is just a row of the table right here. We're walking from 0 to 8, or 0 to 7, right? While I is less than 8, so I plus plus. So we're walking through this row here, looking for unvisited neighbors. So we see neighbor A, which we haven't visited yet because it's not marked, right? It's not visited, and what is this? And graphs of node lists of it is a neighbor, right? I'm checking is graph sub row 2 sub column I. Is there a 1 there? I'm checking. Is there a 1 here? I'm checking. Is a neighbor of C? And it is, and it's unvisited, right? So we mark A's parent as C, the 2 that we passed in here. We mark tree sub 0, which is this guy. We mark it with C, and then we call traverse recursively. So we come back into this with A in here. Okay, then we're going to go through A's list. Right, we're going to walk through this loop through A's list. We're going to go down these guys here looking for an unvisited neighbor. So this guy is not a neighbor. This graph sub node list sub I is not a graph sub A sub A. A is not a neighbor of A. That's what it says. So you go on to the next guy, and here B is a neighbor of A, right? This would be node list sub. This would be we're looking at A's list, and we're looking at neighbor B on I iterator. B's a neighbor, and B has not been visited. This would be false for B. So we mark B's parent as A. That's this tree sub I equals node list. Then we push, we call traverse again. So we'll study this, but the tree looks like this. See? We start off in main here by pushing. I'm using the term push, even though what we're really doing is starting this traversive call. So we push the 2, or in this case a C. C is 2. That's this box. And then we mark that C has been there. That's this visited increment, or make a mark on this visited array. Then we go into this while loop looking for an unvisited neighbor, and we find that A is not been visited. So we call traverse for A. So we call traverse for A here. Comes back into a new traverse, right? Comes back into this traverse function, but for a brand new instance of traverse. And A is the parameter here. We're traversing A, or we're calling traverse for A, right? So we mark that A has been visited. Then we go into A's list here, looking for an unvisited neighbor, and we're looking for an unvisited neighbor. That's this logic. We find that B is an unvisited neighbor of A. So this one here, this one, and so we push, we push B by calling traverse. So we get another instance of traverse. That is, we're coming back into this function again for traverse, for B rather, right? Then we're going on to B's list, and we've visited A, we visited C. We're going to look at these other guys. We're not going to find any neighbors on B's row, so we're going to return, which is like a pop. Okay, and then we're going to pop all the way back to this. Then this is going to find D. It's the last unvisited neighbor of C. So we're going to call it's going to call traverse with D and come over here. It's going to look in D's list and find E and go over here, and it'll find F, find G, come back to F, find H, come back, then pop all the way back to here. Okay, so this is the graph, and you do get the same tree because you're going to, even though there's a link here in the data, you still get the same tree because C finds neighbor D before it finds H. So it's going to go this way, then it's going to go E, F. It's going to go all the way to G and then to H and then back. And then when it gets to C, it won't do this link because it came down this way and found H already. H had been visited already. Okay, so the first thing you need to do is study this code, right? And map this in your mind to this recursion diagram. Okay? And understand the way that the data is being stored in this visited array and the tree parent array. Okay? Get that all down in your head. That's the first thing you need to do. Before I go on, I wanted to point out that, where's my stack? See this stack execution thing? Where it goes from C to B and then down and then comes out to G and then down and then H. It looks like the tree. It looks like the recursion tree, right? You start off at main, you go all the way to B. So you push A, push B, and you come back, right? Then, so that's down to here when you're coming back. Then we're going C to G, so it's C, D, E, F, G, then back to F, then to H, then F, G, E, D, C, like that. So a recursion diagram is a lot like this stack algorithm here. It's good stuff. Okay, so I hope you're following what I'm doing mostly, but study it. Make sure you understand what I'm doing here. And then what I want you to do for the homework, I want you to do some changes here. So part one, study this graph CPP until you understand it. Then change it to use this graph. Graph 2. So I've given you graph 1 text. You could make a file called graph 2 text and set up the ones and zeros appropriately, or you could just get into the source code, wherever that is. The source code. Now here it is. You can get into the source code and just change this table for the new graph, right? Because right now this table in the code is this graph, so you could manually hard code this. But really, what you should do is get this file working, okay? And because I've given you a function here called fillofile that just fills up this 2D matrix from a file having this format. But the reason I want you to do that is because the next thing I want you to do is do this graph. There's a really big graph here. But back to the instructions here, right? So get it to work with this, which it does already. Then modify the data in the code or the file to work with this graph. Then I want you to make a diagram similar to this, but for this second graph. Okay, because it's really important that you guys learn this recursive technique. I've been looking at your homework. Most of you are doing this recursive thing okay, but a few of you still aren't. And you really need to understand this way of making diagrams because, you know, it's a particular way that will help you understand recursion better. So this is one more chance in the class for you to work on your recursion diagram skills. All right. So make a graph like this, but for this other graph using node. I think I specify which node in here. Use node A. So start with this node here. Like here we started with C, but for this new graph, start with A. So that means in main when you call off traverse, you'll just you'll push an A. You push an A here instead of a C. Okay, that's part 3. Okay, then part 4. I want you to read this into data. So you need to make this bigger. This is 8 by 8. I think this is 80 by 80. Count it and see, but you're going to have to make this array bigger. You'll call fillofile with biggie graph, and you'll fill up this giant, 80 by 80 now matrix, and then start it off by pushing. I think I say which one to push. Use node A. So start off by pushing a 0, or call traverse with 0. Right? And you're going to get an output sequence that is your answer. This thing here just prints the node. So it prints this. For this graph, it prints, this print node is going to result in C, A, B, D, E, F, G, H is the sequence that you're going to get. In fact, you could number these. This is first, this is second, this is third, this is fourth, this is fifth, this is sixth, this is seventh, this is eighth. That's the sequence that you're going to get. So you'll get a different sequence for this little guy, but I also want you to draw the tree for this little guy. And then you'll get a big old sequence of 80 nodes for this guy. But I'm not asking you to draw the recursion tree for this big graph, right? That would be like crazy. Okay, then the other thing I want you to do is keep track of the longest path. Let's go back to this thing, this graph. The longest path is this one. Or this one, they're both the same. This one's 1, 2, 3, 4, 5, and this one's 1, 2, 3, 4, 5. Keep track of that. So the easiest way to do that is every time you call traverse, when you come into traverse here, increment a counter. Put a counter in here. It'd have to be a global counter or a static, right? Something that remembers its value between every call to this traverse. Increment it. And when it and then keep track of the max, right? You'll have a global max variable and then a global counter variable. And when counter exceeds max, you've got a new max. So then store what's on the stack. So the tricky part is you don't actually have a stack because you're using the call stack. You're just doing this recursive business here. So the easiest thing to do is just make another stack. So that's what I'm saying by method A here is keep a separate stack. Okay, so keep a global counter in the first line of traverse here, put a global counter, and increment it when you come into traverse, and then decrement it when you leave traverse, just before you leave traverse. And then keep a separate global stack and also do a push up here and a pop down here to that global stack. Then when that stack reaches a new max, so you need to keep a value up here, a global max. When you get a bigger max, take your stack wherever you're going to have a global stack and copy it to an array. Okay, you could just use an array and treat it as a stack for both of these things. However you want to get that working, it doesn't matter. You know, you could do. You might have to implement another. I think you'd have to treat the array. You'd have to treat the stack like an array so that you could copy it. Or you know what you could do? You could make a stack copy operation that's like part of your stack or something like that. Anyway, figure out something. Okay, and then when you're all done, print max stack at the end. All right? Method B is a little trickier here. It involves using pointers on the function call stack. So, you know, if you have an interest in that and you've messed around enough with pointers and in C, you know, you'd have to be, you know, pretty solid in low-level C stuff. You know, way low level, like pointers on the call stack. If you feel like messing with that, that'd be fine. Like sometimes in an assembly language class, they make you deal with that low level type stuff to help you do assembly. But anyway, I'd recommend method A on there. All right, that's the assignment. It's a little bit of implementation. It's basically getting what I've written here to work, which should work already, barring any slight version differences with your environment. But get this thing working, modify it to work with this second one, draw this diagram for the second graph, and then get it to work for this gigantic graph, and just give me the output sequence of print nodes. All right.